Finally, Verify Trig Identity Day is here. There's nothing new for me to show you, just a bunch of calculations to prove or verify that an identity that's been given to you is a true identity. So let's get started because I just can't possibly wait longer. So the cosecant of x, cotan of x over cotan of x plus tan of x equals cos of x. So this is obviously not the kind of identity that we've been working with where I tell you that it's true and you have to memorize it or be able to work with it. This is a special case, but we're going to use all those other identities in order to prove that this is indeed an identity, meaning that this side of the equal sign is equal to this side of the equal sign. So here are some little hints along the way. There's only one way to do this, and that's try to use your predictive minds to see what the next step or where you might be headed, and to use some little tricks that I'll share with you. So first thing you want to do in a case like this is start with the ugly side. We're going to convert the ugly side to the pretty side, and if we're able to do that, then we know that we have solved or proven this identity. So first, in this case, I want to turn everything into sines and cosines. So cosecant is 1 over sine x over cotangent is cos x over sine x plus tangent is sine x over cos x. And I think this is where we are right now, is the reason so many of us hate learning identities in the very beginning, because they turn to fractions that we have to work with. And we've spent so many years of our math lives trying not to do, believing that at some point fractions would become obsolete and we wouldn't have to work with them. But indeed, that is not the case. So I'm going to go ahead and use a common denominator, which would definitely be sine x times cos x, and I'm going to multiply across into the opposite numerators. I'm going to keep the numerator of my identity, or my left-hand side, exactly the way it is. And I like to use a double line when things get messy. So I have cos squared of x. I kind of like when I get that because I have that great Pythagorean identity, plus sine squared of x all over sine x cos x. So before I start applying identities, I'm going to work to make this less. So I'm going to take 1 over sine x, and I'm going to multiply that by the reciprocal of the denominator, sine x cos x over cos x plus sine x. Well, I guess cos x plus sine x just equals 1, so I can do that. Then I can get rid of that, and look what I have. Cos x, proven. I actually got there faster than I thought. I thought I had a couple more steps. So proven, done. Let's do another one. This time we want to take 1 over sine y minus y. Excuse me, sine y minus 1 minus 1 over sine y plus 1 equals negative 2 secant squared y. All right, this mother's face factoring, right? This is a difference, a sum and a difference of binomials. So find a common denominator means multiply each numerator into the opposite denominator. Each denominator into the opposite numerator. So I have sine y plus 1 minus, parens to protect my negative in case there's a distribution issue, sine y minus 1 over, this is sine squared y minus 1. Let me check my arithmetic real quick. Sine y plus 1, sine y minus 1, difference of two squares, or sum and difference of binomials, distributes to give me a difference of two squares. Done. Then if I distribute my minus sign, that means change the signs inside and turn it into addition, and now I can disregard the parentheses. Sine y minus sine y, those cancel. 1 plus 1 equals 2. That's looking good because I kind of want a 2. 2 in the numerator over sine squared minus 1. Remember, we have sine squared x plus cos squared x equals 1. So sine squared x, or cos squared x, equals 1 minus sine squared x. If I factor out a 1, then I get this version, right? So this would be 2 over, factor out a negative 1. I factor out the negative, and so I can reverse the order of these and the sign. 1 minus sine squared y, and that gives me negative 2 over 1 minus sine squared is cos squared. But that's negative 2 secant squared of y. I have proven my identity. So I think I'm just going to keep going till I run out of time, because the truth is, when you're learning identities, the more examples you can see, the better. So let's prove sine cubed x minus cos cubed x equals 1 plus sine x cos x times sine x minus cos x. So sometimes it's a matter of picking the right side. If I look at this side, I could factor this as a difference of cubes. That would be easy enough. But what if I don't remember the difference of cubes? And I'm guessing some of you guys don't remember the difference of cubes right off the top of your head. On the other side, I have distributions. So I'm going to go ahead and start with the other side, because I think it's actually going to take me to the left-hand side faster. So first I want to distribute 1 times sine x is sine x. 1 times negative cos x minus cos x. And now sine x times sine x, or positive sine, and cos would give me a plus sine squared times cos. And then the last distribution, positive and a negative, is a negative. Sine and 2 coses would give me sine x cos squared x. And I need to, nope, I don't need any of these parentheses. All right, so now let's combine. Well, I have a sine x, and I can't do any canceling. And even though it doesn't necessarily seem obvious, the best thing I have to work with is a sine squared and a cos squared. So I'm going to convert these using the Pythagorean identity. Sine x minus cos x. I might be wrong. It's okay, I have an eraser. But I think that's my best shot at this stage of the game. So sine squared is the same thing as 1 minus cos squared of x times cos x. This is looking good, because when I make this distribution, I'm going to get a cos cubed, and that's what I want. Same thing over here. I'm going to have sine x times, that's a negative protecting bracket, so times 1 minus sine squared of x, just using the Pythagorean identity again. Now I'm going to do the distributions. Sine x minus cos x plus 1, not 1, plus cos x minus cos cubed x. Oh, that looks good. Minus, protecting the negative sign, sine x minus sine cubed of x. Change the signs inside, turn it into a plus sign. Now I can disregard the bracket, and I have a positive sine x and a negative sine x. I have a negative cos and a positive cos, and what I'm left with is a positive sine cubed minus cos cubed of x. And that, my friends, is a proof of that identity. All right, let's do another one. let's take tan theta plus cos theta over 1 plus sine theta equals secant theta. And we want to use the trig identities to prove that this is true. In this case, it's easy to see which is the ugly side. It's clearly the left-hand side. So let's turn everything into sines and cosines. Starting with tan, sine theta over cos theta plus cos theta over 1 plus sine theta. Okay, now common denominator, I'm going to multiply 1 plus sine theta times sine theta. So that gives me sine theta plus sine squared theta. Of course, I always love getting sine squareds. And plus cos squared, oh, that looks really good, cos squared theta over cos, well, I can distribute this, but I think I'm not going to, because I think I'm going to end up with a sine theta plus 1, which is the same as this. So I'm going to leave cos theta times 1 plus sine theta. Then in the numerator, this all equals 1. So I have sine theta plus 1 all over cos theta times 1 plus sine theta. Sine theta plus 1 cancels. I have 1 over cos theta, which is the same thing as secant theta. All right, I know I said I thought I was going to run the timeout, but the truth is I'm only at 11 minutes and I've done really enough examples. Everything after this is about practice, practice, practice. So the tricks are: 1, convert to sines and cosines. 2, look for patterns, look for factoring patterns. And 3, get good at fractions if you're not already. There you go. That's it.